Hi and welcome to MSc. In this video we're going to be looking at VSEPR theory where we have 6 electron domains. When we have 6 electron domains around the central atom, there's 3 cases we need to consider, and I will do one example for each of the cases. As always, the first scenario involves all the electron domains being bonding domains. I will do sulfur hexafluoride as this example. As we've seen with other examples, when we got to 5 electron domains, these are all going to have expanded octets. They can be trickier to draw. I would highly recommend listing out the number of valence electrons. 6 from the sulfur, we have 6 times 7. So this is going to give me 42 plus 6 is 48 electrons. So we'll start it off. We have sulfur here, and really there's not much option here except to maybe just place the 6 fluorines around and hope for the best. All right, and let's give the fluorines lone pairs because fluorine's super electronegative, unlikely to lose their lone pairs that they already had, and we'll count up and see what we get. So this has 6 and 2 more is 8, so each of these have 8, and 8 times 6 is 48, and we've drawn it right. No lone pairs needed on the sulfur, but it definitely has an expanded octet. So what will this look like in 3D space? Well, let's take a look at PhET and figure out what the picture looks like. So here it is, sulfur hexafluoride, and we can see that we have lots of 90-degree angles. Well, that's nice. They're nice to draw. And we can see that it's a very symmetrical molecule. It's got like this square shape along a plane in the middle, an atom above joined by a bond, and an atom below. But it's so symmetrical that I can draw it any which way, right? This atom here that's on the side, I can move to the top and it all looks the same. All the bond angles are 90. This shape is called octahedral. And it's called octahedral because if this was a solid, it would have 8 faces, just like an 8-sided die. Going back here, let's see how we could draw this out. Well, I have my sulfur, and I certainly can have 1 fluorine above and 1 fluorine below. But now I need to kind of draw the middle 4, which means I actually have 2 that are coming out away from the sulfur, and I'll draw a wedge there. And then we have 2 that disappear in behind. So this is supposed to look like the middle plane with 2 going in behind and 2 coming out. Something like that. Again, our picture isn't perfect, but we made an attempt to show some of the depth that occurs on it. Again, for this to be a formal Lewis diagram, I need to add all the lone pairs, and dashes as lone pairs are definitely faster than 2 dots or X's. Don't forget that we found out too that all the bonds here are all 90 degrees. Even the ones that don't look like they're 90 degrees, they're all 90-degree angles between all of these. And between the ones here as well in that middle square. Also, as we saw from the PhET simulation, the electron domain geometry is octahedral. And of course, because the electron domains are all bonding domains, the molecular geometry matches the electron domain geometry. The second scenario is where we lose one of those bonding domains and it becomes a lone pair. 5 bonding domains, 1 lone pair. The example we will use here is bromine pentafluoride. We'll start with the bromine in the middle, and we'll draw 5 fluorine all around. We will draw lone pairs on all the fluorines, and we'll see if that matches the number of valence electrons we have here. So bromine is going to bring 7 valence electrons. We have 5 times 7 here. So this is going to give us 42 electrons, valence electrons to place. Each of these fluorine and bonds is 8. 8 times 5 is 40. We're missing 2. They have to be on the bromine. I'll draw them down here. That's where I think I have the most space, but also going to lead to the next picture as well. So again, let's go to our simulation and see what this looks like. I'm going to select bromine. Here it is, and here's our picture. We can see the lone pair. Now, because of the symmetry originally with 6 bonding domains, it didn't really matter which one we replaced. Here they've replaced the one at the top we can notice again that the angles all get slightly compressed. And we can spin this around to get a better view of different parts. And all the angles get a little bit compressed because of the electron density here. I drew it in the picture something kind of like this, where I drew it on the bottom. The name of the shape of this is now square pyramidal because it has this square pyramid structure to it. Notice, as always, the electron domain geometry is still octahedral. So let's see if we can redraw this to match the simulation. So we will have bromine here with one fluorine up above. Then we will have to use our dashes and wedges. So here's a wedge with a fluorine coming out, and I'll draw another one on the other side. And then we will have the dashes to indicate the ones that disappear in behind. And we'll draw lone pairs on everything to finish the Lewis formula. We can see our square structure. Now my picture is not as good as the simulation certainly, and we can't forget our lone pair on the bottom. So this is our square pyramidal, just like we saw in the PhET simulation. Again, the electron domain geometry remains unchanged. Lastly here, don't forget that these angles have been compressed, and they're now all 84.8 degrees. So understanding that this lone pair pushes them all slightly more towards one another, thus reducing it from the 90 degrees, is important. The last example is 4 bonding domains and 2 lone pairs, and for this we'll use xenon tetrafluoride. Now, xenon is a noble gas, as you know, and doesn't really want to form bonds, but fluorine, being so electronegative, can swoop in and share some of its valence electrons. So here we've drawn our 4 fluorines, lone pairs for the fluorines certainly, and then we can count and make sure that we've drawn this properly. So xenon is going to produce, or bring 8 rather, valence electrons, and we have 4 times 7 for the fluorine. That's going to be 28 plus 8 is 36. Down here though, 8 electrons times 4 is 32. I'm missing 4 electrons, and that is the lone pair on the xenon. Remember, xenon has 8, so 2, 4, and then 1 from each of the bonds is that's 8 electrons. So let's take a look at the PhET simulation and see how well we've done with this picture. So they have xenon tetrafluoride, here it is, and yeah, it looks pretty square to me. And it's called square planar shape. Notice that all the angles are back to 90 because we have equal repulsion of the 2 lone pairs. They're situated on opposite sides because they want to get as far away from each other as possible because they have more electron density and greater repulsion. So square planar shape, you can see it's a flat molecule, and you can see its square shape as well. Sometimes you'll see this redrawn with the wedges and dashes. I don't think that's always necessary to do because it is a flat molecule. It's square planar. This is a little reminiscent of the trigonal planar, that flat molecule that we saw all the way back with 3 electron domains. And as always, the electron domain geometry does not change. It's still octahedral because the only thing that will change it is the number of electron domains in total. And here we have 6. 2 are lone pairs, and 4 are bonding domains. I hope this run through of 6 electron domains in VSEPR has been helpful. If it has, please consider liking the video and subscribing to the station. And as always, thank you very much for listening and watching.